I think there is an option from.
Let's start.
Okay. Satyankar, two slide down. Slide down. Huh? अच्छा, ठीक है. Hello sir, myself Shresth. I'll be presenting the paper Neural Optimal Transport. It was published at ICLR 2023. So yeah sir, because
maybe we can open the PDF in Chrome. That would be fine. Usually,
this is which tool?
open using Adobe, so maybe just Chrome or Edge.
Okay.
Yeah.
So sir, I'll start again. So hello, myself Shresth. I'll be presenting Neural Optimal Transport paper, which was published in ICLR 2023. This is how the entire presentation would go. First, I will introduce what is optimal transport, what were the previous work that was done on optimal transport, and how this paper actually improves it and all, and how it comes with a more optimal way of to learn the transport instead of just estimating the cost function. So if I have to talk about optimal transport, so optimal transport basically refers to learning a map between a distribution X to distribution Y. It has to learn the best optimal way to transfer from X to Y. So in order to formulate that, in most of the optimal transport problems, the cost function is defined, which basically refers to how much of basically numeralizes the amount cost from transporting from X to Y. In most of the previous works optimal transport, it is mostly done to minimize the cost. Nothing has been talked too much about learning the actual mapping from X to Y, because if we know actual mapping from X to Y, that would help in a lot, because for example, there could be certain images which could be regenerated to the original image from which it was created. So in that way, learning the optimal transport map was a crucial thing. So this paper comes up with a good method to do that. So these are certain applications where optimal transport is used generally. Mostly it is used in generative modeling and measuring distances between distributions, which has a wide application among like measuring distances between ideal data sets when choosing while training and all. So if I have to talk about the challenge of learning optimal plans is that minimizing the cost functions becomes easier because you get to see the distance. But for learning optimal transport, you have to try out a large number of functions. If you go by the naive way, you have to try a large number of transport function deterministic maps, and that would actually lead a lot of compute costs. So in this paper they come up with a specific loss function which helps to learn this very quickly. So this is the contribution slide. So as I already told, like what has been the recent contribution, and for this paper the contribution is that they try to learn the map using neural networks. So what they do is that they actually represent a framework of actor critic model, where they try to, like, there is a critic which assigns I'll better explain it in the next slide where the loss function is defined. Just before, so before coming on to this, strong optimal transport and weak optimal transport, I have to just give one thing. So when you are learning an optimal transport map between two distributions, say X and Y, there could be two types. One could be a deterministic map and another could be a non-deterministic map. By deterministic, I mean that every input X is just mapped to a specific input Y in the output. So this could be like when you are talking about image generations and all, this instead of like generating similar images, it tries to replicate certain, for example, this color gets mapped to this instead of having a variety of mapping. So this is strong optimal transport, where you do deterministic mapping, and for weak optimal transport you try to map it to a distribution instead of just a fixed single point Y. That gives an upper H, and the optimal transport plan, which is presented in this paper, learns both the weak is actually formulated on both weak optimal transport and strong optimal transport using a gamma factor. So if I have to explain the loss function, so for strong optimal transport, just the WP distance is taken simply because you are mapping it directly to a particular point. So that works for strong optimal transport. For weak optimal transport, in order to calculate that distance, this is used. This basically refers to cost of mapping x to a conditional distribution of pi given x. So all those points in the map, my output space, we take a conditional distribution on that, and then we minimize this cost function over dx over all the x elements. So this is the picture. Like this denotes the deterministic map, and this denotes the how like non-deterministic maps work, how the stochastic maps work. Every input is mapped to a multiple of y values. So this is actually the main heart of the paper that comes into that, like how it actually learns the optimal mapping. So this is the cause. So here, what is f? F is basically a critic function. So if I have to explain this first before going on to the math, if I have to explain it in very briefly stuff. So f is a function that assigns weights to the real values of y. For like in your when you're transporting x to y, the f assigns how much actually you transported that to the y. So f tries to minimize the maximize the values that it assigns to the real data and minimize the value to the generated data. So with this critic model of f, the paper, what it does is that it tries to learn another transport function which acts opposite to the critic. Like this critic wants to reduce the weight on the generated data, but the transport wants to increase the weights. So the loss function, if you see, is that like it is formulated like this. So this is the loss function for the optimal transport map, because it wants to minimize this cost of transporting and also wants to like maximize the weight assigned by the critic function to the generated data. T of z denotes the generated data of the function. So in this way, the map actually learns. This also about the noise factor. This is for this noise factor. This comes for the stochastic map. So as I told, like there could be two mappings. One could be the deterministic one, and one could be the non-deterministic one. So in the deterministic one, there is no noise model. Like in the previous slide, I would like to say that like one thing that challenge like learning a deterministic map was pretty like just for using this cost function you can learn deterministic maps easily, but when you had to learn non-deterministic mapping between the x and y, they came up with a heuristic of sampling a noise from a general distribution and adding it to the a transport map x and then mapping it to y. So in that way, the single input x with some noise gets mapped to different points. So in this way, they try to replicate that stochastic map. Like instead of trying all possible different t functions which could transport z to different, like for input x, there could be multiple t functions which transport it to the output space. So instead of learning all those t functions, they came up with a heuristic that better it would be to sample z points from the distribution, from some distribution, add it to the transport map which is learned, and then actually transport it. So,
but the sampling is based on a potential, right?
Yeah.
Which is not completely learned.
Yeah.
So there's a chicken and egg problem here. So.
But here that is actually a critique of the paper. They assume the distribution to be like in a earlier formulation and experiments also. They assume that Z is some Gaussian noise, and then they add it into the X and then they map it. So in the appendix, they have written that these are the critiques that they could be formulated. So this is one definitely the critique of the paper. So this I talked about. Yeah. So finally what they come up with that was this, the cost function of this. So this is the main cost function of the entire paper, which is trying to minimize this loss function over optimal transport T plan, and the critique function, which is the F, is trying to maximize this. So if I have to just like what I told, if I have to tell what this critique function is, well, what this loss function actually simplifies. So this is the weight that the critique function assigns to the real data. So for the critique function, he wants to maximize this weight, and this is the this term basically means that it wants to minimize this cost function and maximize this weight generated by the critique to the transport map. So for the transport map, he wants to minimize this. So in this way, the training is done and the transport map is learned using this good heuristic cost function. Yeah. So these are the specific things that are used in the like it's just to summarize how the NOT algorithm finally gets trained. So we have this parametric. They define the critic as the parameterized potential F, which maps Y to R, basically assigning weights to the real data. And then we have a stochastic map with some parameters theta, which is learned like that. The next page has the algorithm. So I'll explain the algorithm better with the pseudocode. Yeah. So what they do is that for they at every they do it in batches, like they have to so for every iteration they sample y from the queued output data x, and for each x they sample a zx from the distribution which they assume, the noise distribution which they assume. And for that, first thing they do is to learn they backpropagate the critique function. So this is the loss function for the critique function. He wants to minimize this loss. Why? Because he wants to minimize this average critique value that it assigns to the transport map. That is his goal, because he wants to minimize the amount weights assigned to the generated data than real data, and he wants to maximize this weight assigned to the real data. So this is the loss function of the critique function. So at the first step, this is back propagated, and the cost function is critique is learned. Now instead of just doing a single training for the transport map, they take KT iterations. Now this is again a parameter which they further tune probably they have in the appendix. So now they come up with this loss function LT for the transport map. So again, this loss function tries to minimize this cost of transporting X on using this transport map to the output Y, and maximize this. What is this? This is basically the critique, how much weight the critique is assigning to the transport map. So it's like a two-way fight which is happening between like the critique and the transport map. And then they update theta using this back propagation. So in this way, this is done, and the weights are learned, and the optimal transport map is learned through this. So yeah. So now comes how the optimal, how the like this heuristic, how did they learn with the both the stochastic maps and as well as the deterministic maps. So for that they use two loss functions. So for strong cost they simply use the cost function with some without any without any addition of some variance. But for the weak quadratic cost, that is the stochastic distributions, they added this term, which is basically a variance term in order to track the how much the input x is getting, like what is the variance of the mapping of the input x. So that introduces a stochastic nature in the transport mapping, and using this loss function they learned the non-stochastic stochastic map, and the first one was just for a deterministic one. So all of this comes in the algorithm. They place this and do that, and this is the theorem which they had.
So in the strong cost case, they need to also round off, right?
So round off in the sense?
Round off the solutions. They'll have to discretize, quantize the solutions. The strong cost. Yeah. But what is the loss incurred because of that? Is there some theoretical analysis? Is Monte Carlo sample Z? So it's just based on sampling. But isn't there the strong cost requires some rounding off, discretization of the solution you get?
In the paper, they had not yet, not very specifically talked about discretization. They mostly mentioned that the use of the cross function in the algorithm that I mentioned earlier. And now how to learn this T theta map, they use neural networks and prove that neural networks are universal approximation of stochastic transport maps.
But the neural network is learned even for the strong cost, right?
Yeah, yes.
But then the map in the strong cost case is all discrete, right? It's 1-to-1. It's not stochastic. There's no distribution.
Strong cost is 1-to-1.
Right. And how is the T learned in the case of strong cost?
So strong cost, the loss function as I told is simply the distance map, no? In the strong cost, this law is simply in the strong cost they simply learned just took the at every sample size they just took the differentiation like back propagation and learned the direct mapping. So since there was no this term, they ensured that it gets mapped to single term. So it's simply the SGAD algorithm. Okay. like this is some how the prior work was and how the NOT paper improved it. Like they and NOT like this was some earlier that was used to learn the like as I told in the earlier that there were very few applications where the fixed transport maps were used, but NOT generalized it to more stochastic and weak cost too. Like earlier there was some work on deterministic, but this paper generalized it to more stochastic maps and weak cost.
So I was just thinking the entire iteration, outer iteration is very consistent with curriculum also, right? Sorry? But the papers are not treating curriculum as an application. The curriculum is very natural application. I mean, even this team won't look at curriculum. I don't know what your project is, but yeah. Not one team?
Yeah, one team. The Nurips paper was different.
Yeah, so as part of the course project, you are together or?
Yeah.
Then you make a data mixture.
Data mixture for the IBM people.
They didn't calculate as properly or
yeah, like we had meet with the people, but like they said that they will allocate us our work in 1-2 days, but we tried to connect, but they didn't like. We were not getting active work, so we didn't. We are actually not clear like for the data mixtures what we have to do actually.
Yes, let's talk after this.
Okay, okay, thanks. So now this is the experimental setup which they do. They try it with gamma 0 and gamma greater than 0. Gamma greater than 0 is simply basically with a stochastic mapping, W2 with stochastic map, and gamma 0 is the deterministic map. And I'll just quickly run over this. So with gamma 0, the training with strong curve leads to conditional collapse, becomes independent of the, which is like fairly intuitive also. Like if you're doing a deterministic map, the noise would not make any difference when you're trying to learn it from X to Y. So that is one thing which they discovered, and this was done in an MMR paper earlier to learn the deterministic map. So that thing collided. That means their formulation was correct. So yeah, and for so this is the mapping with gamma equal to 0, deterministic mapping. Okay, so yeah, so experiment, so we can, so it's the same experiment, the same paper which is on site. Okay, so finally, if I have to summarize the paper, so this NOT provides more sound framework, complete framework, but it has some critique that is not completely sound, which would be discussed by my team, Mr. Satyankar, about the further discussions. So, thank you, sir.
The mic off.
Okay.
Oh. Hello. Yeah. So Shresth gave a good overview of the main neural optimal transport paper. The paper I'm going to be presenting is on kernel neural optimal transport. It's basically, it was a part of ICLR 2023 as well by the same authors, and it's basically the sequel to the previous paper. Like as Shresth hinted off at the end, the maps, especially in the basically in the weak OT formulation, the NOT, the neural optimal transport presented in the last paper returns basically if you keep varying the stochastic generator S, then it returns all the possible maps. I mean, there are obviously like there are multiple possible maps with the same like lowest cost function, but it can basically it has completeness. If you keep varying S, it will return all of them, but the soundness is not there. So basically, the main issue is that if we are looking at weak optimal transport and then we are applying the NOT algorithm from the last paper, then the map T star which is being returned, it might have, it might be a false positive and have like fake solutions, and we'll get to the details of that in this paper. So I'll not go through all the details again since it's pretty much done, but I'll tell the main thing which is required for this particular paper. We are now focusing on the weak cost function itself. So there are, in the dual formulation, Shresth has already shown there are two components. One is just you want to minimize this sort of direct, like the direct distance between x and like over the x and the distribution to which x is mapped. We want to minimize the distance between those points, like the expected distance. And then there's also diversity term. So that depends on a hyperparameter gamma. If we increase gamma, then we are allowing our map to be more diverse, as in we are allowing x to be mapped to different sort of samples for y. And this hyperparameter is really useful in real life because uh, yeah, there are some good practical considerations which I'll just show. And the main algorithm like is still the same as the last paper. There's no changes to the cost function. It's still there is still a critic which is like this f, and there's still the map which are which the neural network wants to approximate best so that the cost is minimized. And again, uh, as it was done last time, it is still done using simple stochastic gradient descent. Right till now, like there have been no sort of changes. Yeah, now we come to the main part of this paper. As Shresh pointed out, one of the main arguments and one of the lemmas which the neural optimal transport paper proved is that every stochastic map which you recover from their algorithm, uh, that uh, like this thing holds, like it's going to be belonging, like it's going to set the cost function to a minima, like it's going to be one of the argmins. But the problem is that not all such solutions are guaranteed to be OT maps. So the cost will be minimum. They will like you cannot lower the cost further, but they will not be like OT maps by definition, in the sense they will not preserve the distribution, like uh, either the probabilities will not sum to 1 for every x, or the conditional distributions will be invalid in some sense. And this paper asserts that we can improve, instead of considering a simple the gamma weak quadratic cost function we just saw in the last paper as well as this slide, we can consider a kernel based weak cost function, which actually gives this assurance that all the solutions you find from here are both complete and sound. So this paper actually, like, that's how it improves on the last paper. Yes, yes. So last time they have only showed the completeness. If you keep varying S, then you will end up with you will recover all the solutions eventually. This time they'll prove the soundness also. So last time the soundness was not there actually, so it can't be proven. In the yeah, they didn't. Yeah. So the curious thing they actually pointed out in the last paper was that sometimes we are doing training. It turns out the training is a bit unstable and it's leading to weird results, and we are not able to quantify at this point why it's happening. But in this paper, they have mentioned that this is probably one of the reasons that not all the weak quadratic functions are sound. So that's why the training is affected, and we'll discuss that right now. So even when the soundness was not guaranteed in the last paper, why still consider neural optical transport as a viable thing? That's the main idea, is that it's still, even if it's 90% sound per se, it's still very useful in real life because of the diversity parameter gamma, which we can tune set to be anything. So like when we were having gamma equal to 0, means no diversity or variance in the distribution. This is basically the deterministic, like every time all outputs are the same, doesn't really change with z. But as you keep increasing gamma, the outputs start changing, and sometimes we want this behavior. We want multiple, like we want, yes sir, we want more diversity in our outputs. So that is why NOT is still useful, and if you can improve it, it's all good. Now
I mean, how unsound empirically?
Exactly. Yeah.
Some unsoundness.
Yes, sir. So they have touched upon this topic, but
The fake solutions.
yeah. So the thing is, sir, they have shown a particular country sort example per se of a fake solution appearing. But one of my critiques at the end, which I was going to say, is that they have not quantified the fakeness or the unsoundness of the problem itself. And I think that is something which can be done in this paper. So first, let us just see the fake solution, how it appears. Basically, what happens is, say they consider the P and the input and the out, the domain and the range sort of distributions are This is a 2D Gaussian with a lower variance, like 1 by 4 of the, like, yeah, 1 by 4 factor is just the difference. This output is one with higher variance. Now, so this is a stochastic map because gamma is half, 3 by 4 and 1. As you can see, so what this plot shows is for every x, there is the barycenter of the output distribution of x plotted to. So here it's plotted like this. And if you see, like the whole sort of set of points mapped tx comma z, so the actual points for, so like this is a many to one mapping. Now you can see this is actually resembling the expected, the Gaussian distribution with a lower variance. So this is working fine. But what happens is that as you increase gamma, due to the cost function we have formulated, the with higher values of gamma, the distribution doesn't look at all like what we were expecting. So this is in some sense a fake solution. And the other problem, so one thing is that, yeah, again, the cost is still minimized, but now the map learnt is wrong.
From visual inspection, how do you know it's wrong?
So these are directly like the map points. Like, I mean, obviously it's not very, and this is cherry picked example, but here you can see, I mean, these two look really, really similar. I mean, much similar than the other two. Like, uh, this sort of two clusters have started forming. This is not correct. With the barycenters, you can't comment anything. The means they don't give any, like, this is visually uninteresting. This one shows the difference. Another big sort of checkpoint which they realized ki, okay, something wrong is happening is in their algorithm. They saw that even after 10,000 steps, within a span of 300, 400 steps, the maps were changing considerably. So this should not happen. Like they were expecting convergence at this point. I mean, around 10K, maybe they were like 10K is a hypothetical number, but for this data set, they were expecting that the distribution would converge. But as you can see, 10K plus 100, yeah, this is pretty much the same, but now the distribution has sort of changed, and at 10K plus 300, yeah, it has considerably changed from the last one. So they were seeing problems in the training, which they were not able to explain these problems earlier, but with, yeah, that's what this is happening due to the fake solutions or the false positives. And by the way, one more remark which I saw in their appendix, it's like the maps which are being produced, it's not like this is a convex convex combination of correct OT maps. This is something garbage like coming out of nowhere. So it is not useful at all. So we need to eliminate this. So now we come to the solution. How to ensure that, once you find one of the maps, it is implicit, like directly guaranteed to be a stochastic OT map. And the solution they came up with is to have weak cost functions which are strictly convex. So they have theoretically, so this main condition of the paper is this: they have proved this lemma that if you have a strictly convex weak cost function in mu, then this implicitly guarantees that whatever map you will obtain, they are sound. So
where is strong convexity? Strict convexity, strictly convex, weak cost C. How is it helping?
It's like you are applying a stronger condition on the cost function. You are restricting it even more. So mathematically, I mean, there's a big sort of derivation, but it has something. So yeah,
it's existential, right? It implies existence of potential F star, which maximizes the dual figure. So the strong convexity is giving you feasibility.
Yeah, and strict convexity is also giving you the soundness.
Strict convexity is giving you feasibility, and is giving you feasibility. But how is it giving you soundness?
So this is not like, it's not obvious. The proof is like it's quite mathematical. I mean, so I have not omitted. I mean, I have omitted it in the Sanda because like, yeah, it's a bit tricky. But yeah, to me it was not obvious at least. Yeah. So now the big question comes: can we construct strictly convex weak costs? The first thing they take an example of is this entropic cost function, where you have like cxy, which is you can take it as any normal cost, like just simple distance functions, minus some hypervalued epsilon times the entropy of the distribution to which x is mapped to. And yeah, they have proved, so we can prove that this thing is strictly convex. And this will give us all the sound map. But the issue is that we need to again, so to get this h mu, you need to do Monte Carlo sampling again and again. So we have to do numerical estimation. Then the problems come is, one is of accuracy, like how many, you have to take a lot of samples, and second is obviously in the algorithm computation time will go much beyond like what is required. So then they propose that we should try looking at kernel costs, which are much easier to calculate because they can be just represented as like scalar products. So what they do is that this is just simple like kernel level reformulation of the cost functions. Like first, any input will be mapped to a higher dimensional feature, and then the kernel is for some feature mapping you, it's just the inner product of the like feature mapping is applied to the two inputs, and it returns a scalar. So this is the same cost function from the slides earlier, and they just reformulate it in terms of the kernel. So now they get that earlier like C uy, like u was two earlier quadratic cost, so they form it as C k gamma, and these are the just parameters.
So it's similar to maximum mean discrepancy in our cases. Is it after mention something similar to
In similar to what did you say?
maximum mean discrepancy?
Did you see? I don't.
Maximum formulation which I
No, maximum mean discrepancy.
I don't know.
in the
I don't
first
think.
paper there was no mention.
It's like a weighted family distance.
Yeah.
Yeah, that it is, but they are not mentioned or
Yeah,
taken note of that fact. So, but I mean, I don't think they. Yeah, so this is just a summary of the main results of the paper. That if you use kernel cost functions, then they will resolve the problem of fake solutions. But again, there are still some issues. First of all,
But
just some.
you need the kernels to be somewhat non-trivial, right? Otherwise, you can still get.
Yeah, exactly. So yeah, yes, sir, sorry, I should have pointed it out. So first of all, obviously you want the kernel to be characteristic, like it should be able to differentiate between two distributions. I mean, that is one thing. And there are some other considerations which they sort of hint as the limitations of the paper, but again, I'll get to it at the very end, sort of. So yeah, they again for some quantitative results, they found the FID scores to be like lower than like by using the kernel formulation, they found it lower than just the quadratic mean formulation. And as you can see, I mean, although obviously these examples are, they can be cherry picked, but my observation was that you can see here, I mean, maybe this sort of is potentially one row where the weak thing solution is leading to a fake solution, but with the kernel, they are saying that it's working out much better, and the strong OT is always giving a deterministic solution.
The kernel is not going to ensure you have a sound solution, right? Soundness is not ensured even.
Oh,
Is it?
but yeah, yeah, yeah. It ensures the soundness is implied. If you, yeah, right. Uh, for the kernel, it is not very hard to show that the cost is strictly convex, but the implication that if it's strictly convex, then it leads to sound, that is not easy to show. Right. Yeah, so the main conclusion is to use kernel cost, but I have some critiques about this. I mean, first of all, about the practicality of this paper, I think anyways the exact in the like in the if you look at the WGANs or something, then the loss function is just the OT cost. So OT plans, getting the exact plan correct doesn't matter at all in those applications. So I think that limits the utility a bit. But some things which I felt were off, like the qualitative results, the figures they provided in the paper. I mean, they were not very evident. Like I had to make it was not like they were immediately making sense that something is going wrong. So the examples were seemingly a bit cherry picked to me. But the main point, the main sort of critique I have is they are using their own prior work, the neural optimal transport, as the like the state of the art solution for optimal transport, and I'm not really sure if this is correct because in the same conference you are putting two papers, one is building on the
right.
other.
And I think as I pointed to the previous group, I mean, this is the image translation is all consistent with the kind of all cherry pick examples they're showing. But an extrinsic task like data augmentation might be the real acid test. Can all this be used to really
Exactly, that is right.
augmentation?
That is my
Which is
biggest critique with
helping some downstream task. That seems to
right.
be
And so that is sort of my biggest critique with the whole group. The three authors have published a lot of papers, but they are always talking about image to image translation. I'm not sure if the results will hold, right? Because they are not. I've checked their GitHub; they are not simulated it on any other distribution sort. And again, with this paper, this is not a critique per se because they have addressed this as a limitation. They don't know how to choose the kernels well. So, and here the domains for similar images. That if they are not images, what to do is unknown. And also with images, it has been hinted in their peer review that I mean, images are sparse in the Fourier basis, so something else must be happening inside. You don't really know. So like these kind of issues are there. Uh, but yeah, I think that's about it for this paper. One thing I would like to say is that yeah, there is a lot of scope at least for this paper. The last paper was pretty polished. This one it has more work to do. So yeah.
good.
Hello. So now I'll discuss an application of optimal transport in LLM architecture. Uh, yeah, so basically LLM models suffer the latency issues due to the fundamental order regressive nature. There are, yeah, so there have been multiple approaches to solve this issue, and the fundamental, the most obvious one is the speculative decoding one. uh, yeah, so the speculative decoding mostly focuses, they take a large model and they take a small model which has an efficient uh, yeah, so the small model is efficient in producing the sampling tokens just because it has lower tokens, and using that we can map that sampling distribution to the large distribution of the original model, and we try to uh, make the smaller model such that the larger model has tokens which are very similar to the smaller models. So basically the technique is you take a context and put it in the smaller model and generate some tokens of fixed length using the smaller model, and put the whole of the generated tokens along with the existing context into a larger model, and then you try to sample the tokens from the tokens generated by the smaller model using this technique such that the sampling is effectively a sampling from the larger model. So, I mean, this is pretty obvious. Yeah, so basically, what the fundamental idea of the paper is, why not sample multiple drafts at once from this smaller model, such that we can capture more information about how the distribution is based on the next tokens on the smaller model, and maybe it would help us efficiently find the next tokens, so that this L dash is more for the larger model, because this higher the L dash, uh, lower the latency, because we'll have to pass it less number of times to the larger model. Also, to this idea is also based on the fact that you can pass multiple contexts to a LLM, and the latency will be the same due to the batch processing and all. Yeah. So the authors try to connect this coupling, the distribution of tokens from the smaller model to the distribution of the tokens on larger model to optimal transport. Just because optimal transport is most general relationship between any two distributions. And how this works is, let's say you have a distribution of tokens on using the smaller model, and you want to predict the distribution of tokens on the larger model. So for the tokens which are, so they generate a cost like which is indicator function when the tokens are not equal, and which is using this cost function we can so basically if you have an optimal transport between the distribution P and Q, and you have a sample X which you have a sample from the smaller distribution, and now you compute the optimal cost between the both the distributions P and Q, and just like the algorithm says, if the Q is greater than P, then just take the token, and if Q is less than P, take the token with the probability Q by P, and otherwise sample from the residual distribution. So in the optimal transport perspective, what they do is they take the transport map, and given the P, if the coupling matrix of P and Q, if Q Q the matrix X comma X, if that is equals to the P, what does it mean is that basically means that P is less than Q in our algorithm condition, just because this cost matrix forces the coupling matrix to be minimum of P comma Q at the diagonal entries. So then we sample multiple drafts using the smaller model, and we try to learn the optimal map between those set of tokens to the token of the larger model. However, there is no direct intuition how this optimal map would work. Like just unlike the algorithm which was there for the k equals 1 case, there is no direct intuition how would this algorithm look like if you had multiple tokens from P and you want to map that to a token in Q. So, and to learn that, we use the optimal transport map so that it learns on its own, and we use that calculate the tokens on Q. However, if you look, P cross K is the product coupling of K P distributions, which basically is assuming all the P's are independent. And so when we'll try to find the optimal map from P to Q using the linear program, the complexity of that program would be just like the simplex program has a complexity of m times n into log of m plus n, and the size of the distribution of P is this gamma power k, and the size of Q is gamma power 1. So it would be gamma power k plus 1, which is unfeasible for LLM models. So they try to form an approximate optimal map from P to Q, such that the model is the optimal map is correct, but it is the cost is not minimum. So so basically if you have they didn't use the idea of computing the actual optimal transport which was in the previous paper. They it's not related to the previous. They are just using the cost function. However, they are using an approximate version, which was, I mean, I have not seen it before anyway. Yeah, so basically, if you have k samples from a distribution of p, and you try to guess the distribution q from that, there's a you cannot say that the distributions, like you cannot sample, you cannot modify the algorithm which we discussed before, and you sample again and again using the k times, just because the probability accumulates multiplicatively, it doesn't accumulate additively, right? So basically what they do is they assume a factor rho such that those k samples from p is equivalent to sampling rho times from the p, and it adds additively. Yeah, so this is the algorithm. So sample k values from distribution p and assume there's some rho such that given this beta for all values in the vocabulary, you calculate this beta, and basically this beta represents the probability of except in standard case where the rho would be 1, just because minimum of qx comma qx would be the sum of all the diagonal entries in the matrix, and this p accepted is the total probability of accepted given that we have k samples. And this, yeah, so I didn't put it here, but rho is calculated using the equation which is that p accepted is equals to rho times beta, just because this 1 minus beta power k is the total accepted probability, and rho times beta would be the equivalent accepted probability, and we can calculate that rho using any. What? This section? It's experiment. Experiments I will come later. Yeah, there's one more algorithm on how will you sample given the k values. So given the k samples, what you do is you, just like the algorithm one, you sample ni values, and you calculate this inequality, and if it fits in the inequality, sample xi, and if it doesn't fit in the inequality, you sample from a residual distribution. This residual distribution is different from the previous one. However, this p accepted by beta is equal to rho in ideal case, just because we have used that rho, and this 1 minus p accepted is similar to the previous algorithm one only. Yeah. Yeah. So now how would you sample from all the k drafts for the large model? This is basically an algorithm. You take L length token length from k drafts of L length from the smaller model, and you compute this optimal transport map, which is approximate for those k samples. And these are basically the casework. If L is equals to 1, then you just sample y from sz, where sz is the multi-set of next token drafts. And basically this is just a casework. One thing I forgot to mention, rho star, which is the optimal rho, can be computed in O of size of vocabulary into the log of k minus 1, which makes it feasible for LLM applications. Just because vocabulary size is much smaller than the total number of tokens. So this is an example of how the iteration works. So basically, you take the context and put that in smaller model, generate k drafts from the L length tokens, and put all those into the larger model, and uh, this algorithm is run at each L step.
Whole idea of speculative decoding is to make it computationally
Yeah.
multi-token prediction, etc.
Yeah. So basically,
So there is, I mean, is it just adding a lot more computational complexity to something that is supposed to be?
so even if we get a slight improvement in L dash, may that would I mean that would overcome the factor that at each L dash step we are taking of vocabulary size complexity, right? Because the worst complexity at each
I feel, I mean, what even so, Bhagwan, who's also Bharat, he's been looking at speculative decoding. But a natural problem is that there is also data mixing. Without data mixing, I mean, none of that works. So, if you can work with Shravan, you guys are doing your course. Which year are you? You have 1 more year, right? The idea is, as part of the project, we could also result some good research, right? Get the data mixing in place. So Shravan and Buddheshwar said they'll get you immediately. But I feel you should not give up on this. This is a very pertinent track that you have taken up, right? I would suggest dovetail all your OT part on this speculative decoding part, right? But to make it work, you need data mix, even to make this work. So talk to Bhagwan. I have suggested you talk to Bhagwan, you know him. He's also part of the course. He's worked extensively on speculative decoding, got the entire code set up. So talk to him as well. So even this reading will actually be put to good use. So I think bringing this together would be a solid research problem. data mixing in conjunction with speculative decoding. So can you discuss this with them? So I'm see the thing is data mixing is just so that they can get started with experiments. But I feel some of this can be actually useful in. I would not suggest getting into curriculum for that will be a distraction, right? Because this seems a lot more promising. Can you work out the? I already written some notes on the. Right. The other possibilities, I mean, so talking to Bhagwan might be helpful. So, the thing is, as far as the speculative decoding is concerned, we have lots of interesting problems in terms of language constraints, right? The only challenge is to get it to work. I mean, without data mixing, none of that works. That is the main problem we are stuck with. We have a lot of natural language constraints which can be actually put to use. So one possibility is talk to Bhagwan anyways. He can talk to Bhagwan and Durga anyways. I've already marked one. Yeah, so talk to Bhagwan and Durga for the research problem. We have some interesting research problem there, and let's have more communication on that. But to get the implementation part, you will need to get in touch with Shravan and Gundeshwar. Said they'll guide you. So this part, why don't you continue working on as a research problem? But as I said, you'll not be able to get a hand on the implementation without Shravan.
The thing is, we spent a considerable amount of time this time looking at mirror of transfer and related literature, but a lot of it is very much into this theory and
This paper, I'm not
this third paper is something which we have picked up like, not quite. But I mean, it's pretty similar.
But that's okay. I mean, see, I that's why I kept asking you, right? If you were to try and come up with a, this doesn't really give you, or rather, the discrete mapping part is not relevant here in this paper. Right? So those are more from theoretical point of view. That's really nothing. One possibility is you try and see there could be a theoretical angle to this work if that excites you. Yeah, so the theoretical twist to the speculative decoding work, and that would be one small part of the paper, and the large part of the paper would be just injecting constraints for speculative decoding. So talk to Bhagwan. I think there on speculative decoding, there are some very interesting research problems, practical research problems, not really theoretical. Depends on your interest is. What's your interest?
I was pretty interested by the theory, but I realized that like it is not, even the authors are not able to take it to some practical examples for now. So maybe.
So you're a little saturated there. What I
Yeah, like there were not a lot of many ideas where optimal transport.
So just pursue on this thread. Let's close that. That's good. In case there is any insight you got from those papers, and as you pointed out, that's the thing. If you can actually get the data mixing is largely just so that you can get the experiments going. They don't work otherwise. Without data mixing, these experiments won't work. Especially when you're looking at, I mean, you have to bring in multi-token prediction, mixture of experts, all of that. Then only things start working, right? So that's the reason. Like you work with Shravan on getting the experiments running, but please continue this third paper's thread. This is very interesting, and you're getting speed up, right? You're getting speed up, which I think is just by anticipating the next token through a proper distribution, right? Through the mapping that you're actually learning. This is largely inference time. Right? This work is largely inference based on this paper. So if you can have some, can you see this can be used for better, more effective training? The efficiency is the main focus. Can it also kind of result in better effectiveness? Right? By the way, there's a library of draft models. You probably know there have been tutorials more recently, which put together a lot of the literature on draft models and verifiers. How many of these, which draft models and verifiers did they actually experiment with? Only Gecko and only these. Okay, so maybe let's even stick to the setup they have, but trying and putting in interesting constraints would be very interesting for us at least. So talk to Bhagwan for that. And why don't you keep posting messages as you make progress? So I already asked Shravan, and he said um, they'll probably do it by today or tomorrow. Just talk to them.
So, sir, as of now, we communicate with the professor and the placer.
Yeah, Bhagwan on the second this thread.
So, sir, how do we finally formulate the right topic? No, I'm saying right now, most of the WhatsApp chat, just ask everyone because it has to be possible. Because like we want to like we have to make whether the project is working with the data the need there. That is our project, so we have to come up with something out from that. It's just some work, hide work that we have to get the final project and clear it and mind so that we can devote our entire time and start doing.
My impression is the data mixing thing will be essential for you to get any of those. Otherwise, you'll be stuck with the same set of papers which you seem to be saturated with. That is super critical. But in parallel, your effort is certainly not put to waste. That I can be for sure, because this is very critical for mixture of experts and multi-token prediction. So if you can talk to Bhagwan and see that, please talk to him. Right? He's read up a lot of literature in that space. Your OT work, how can it be put to quick effect? Right? And because Bhagwan is going to continue this work, you guys can, when you're in your summer break, also continue this work. He can anchor it with you. So I think getting your implementation running is the first priority. Otherwise, you'll be back to square one. But your overleaf writing will not be only based on multi-token, not be based on data mixture, also the speculative decoding. So please continue on this thread in your overleaf writing. So I put some messages here. So he was saying that previously you were working on LR scheduling. No, right? You're never working on LR scheduling, right? Huh? Power. Oh, you're working power scheduling? That was a conversation, right? You never worked on that, right?
They gave us a different power scheduler and explained what experiment might be run on that and asked us to read the power scheduler. And we presented it also.
But that might be even more tangential to you. Yeah. So shelf the power scheduler. So yeah, I'm quite excited by the third paper specifically. But as I said, to get it going, get the experiments running on data mixing. Okay. So don't get into power scheduling.
So we'll tell us.
They're willing to have a meeting. Just okay.